Welcome back to Control System Lectures. In this video I'm going to continue discussing PID controllers by walking you through a thought exercise that's commonly used to explain PID control. During this example we'll try to use reason and logic rather than math to see how PID controllers and their variations are used to generate the desired system response. For this example you're driving your car, which is the plant, and you use the gas pedal to control the velocity of the car. We'll call the angle of the gas pedal theta, where the angle of 0 is when your foot isn't pressing on the pedal. Now I want to create a real simple model of the car to work off of so that if you want to verify our results of this exercise on your own, you can. We need a transfer function from the gas pedal position to the velocity of the car. Now in real life this is a complicated nonlinear transfer function that's dependent on the car model. However, you can simplify this model by assuming it's just a first-order low-pass filter. And the transfer function for a low-pass filter looks like this, where the output is velocity and the input is angle. So let me explain why this is a reasonable estimate. If you press the gas pedal down halfway, the car would start to accelerate and then eventually settle at some constant speed and stay there. And I can say that any position of the gas pedal, if you held it there long enough, would result in a constant velocity that corresponds to that pedal position. And if you pressed it down just a little bit more, then that speed would increase a little bit faster. But here's where the low-pass filter comes in. If you press the gas pedal down slowly, which is the red line, then the car will be able to change its velocity according to the pedal position, the yellow line. But imagine if while you were driving you started pumping the gas pedal all the way down to the floor and back up. The car wouldn't have enough time to respond to that and the velocity would stay relatively constant. Therefore, low-frequency inputs are passed to the output, whereas higher-frequency inputs produce an output that is much smaller. And this is the signature of a low-pass filter. But our model isn't complete at this point, because no one drives by knowingly putting the gas pedal at a specific angle. You don't think to yourself, I need to go 20 miles per hour, so I'll put the pedal at 10 degrees. Instead, people drive by applying a change in pedal angle. For example, you realize you're driving a little slow, so you change the angle of the gas pedal by pressing it down a little bit more. So our command is actually change in angle over time, which can then be integrated to produce an angle which is the input into our low-pass filter. So the transfer function from the change in the gas pedal angle to the velocity of the car is then combined and would look something like this. So keep this model in mind as we go through the exercises. In this first example, we're going to go over proportional control. The closed-loop control system for our car with a proportional controller would look something like this, where the error is the difference between our reference command and the measured signal. And the error is fed into our proportional controller. Now imagine that you're sitting in your car stopped at a stoplight. And the speed limit for the road that you're on is 25 miles per hour. The light turns green and you begin to press on the gas pedal to accelerate up to the speed limit. Now in real life, as you drive your car to respond to this step command, you're unknowingly performing proportional control. Here's what happens. Initially you're commanding 0 miles per hour, and once the light turns green, your reference signal steps up to 25 miles per hour. At this point, you have an error of 25 miles per hour. And this is a large error, so you apply a large change in the gas pedal proportional to that error, and you press the pedal fairly fast because of that. Now as your velocity increases towards 25 miles per hour, your error gradually gets smaller and smaller, so you gradually slow the rate at which you press the gas pedal. And eventually the car reaches 25 miles per hour, and since the error is 0, you stop adjusting the pedal and you hold it constant. Now at this point we can reason that with proportional controllers, the steady state error will be 0. So with that in mind, try to imagine what would happen if the gain was too large in this example. Now initially the vehicle is at rest, and then the light turns green and there's a step up to 25 miles per hour, same as before. And this is a large error, and instead of pressing on the gas pedal slightly, you floor it because of the high gain, and before you have time to register that you've pressed the gas pedal too far, your car is all the way up to 50 miles per hour. Now at this point the error is now minus 25 miles per hour. So you slam on the brakes, and again before you have time to realize your speed, the car is stopped. And then the cycle starts all over again. And by increasing the gain, you run the risk of making your control system unstable. Perhaps you or someone you know already drives like this, where they apply too much gas or too much brake all the time. If that's the case, then you can tell them that maybe their gain is a little bit too high. Okay, so let's look at another example now. This time let's add the derivative term to the control system, but we'll change the problem just slightly. It's the same start as before where you're sitting at a red light, but now there's another stoplight just down the road that's also red. In this example, you're trying to control your position instead of speed, so that when your light turns green, your reference position, which is where you want to be, steps up from 0 to the position of the next light. In the block diagram, this would equate to adding an integrator right here at the end to convert from velocity to position. And so now this is the new transfer function for the system in this example. Also, your reference signal would change from speed to a position since this is what you're trying to control. So now let's apply a proportional controller to that and see what happens. Again, your reference position would step up to the position of the second stoplight. And since initially your error is large, you apply a large proportional change in pedal angle. The car begins to accelerate, and as you get closer to the stoplight, the error gets smaller and smaller, and the magnitude of the change of pedal also gets smaller. Eventually you arrive at the light, and right when you're there, the error goes to 0 because you're at the position you want and you stop changing the angle of the pedal. So everything's okay, right? Wrong. Not only do you have all that acquired speed, but you're still pressing the pedal down and you blow right past the light. Now once you pass the light, the error begins to grow negatively, and you start releasing the pedal, and eventually you put the car in reverse and start heading back to the light. But you have the same problem in that direction, and you end up just oscillating back and forth. So the next time you run a red light, you can just tell the officer that you only ran it because you drive with a proportional controller, and that's just what it does. Of course, more than likely, the officer will just say, "Tell that to the judge," and is going to hand you the ticket anyway. But you can avoid all of that mess by using a proportional derivative controller. When you add the derivative term to the controller, making a PD controller, you're adjusting the change in angle of the pedal based on the rate of change of the error as well as the magnitude. In other words, you recognize that you're closing in awfully fast on the light, so you'd better start releasing the gas pedal a bit early. It works like this. At the beginning you have lots of error, and you aren't moving, so the proportional path is large and the derivative path is 0. Once you start accelerating towards the second light, the error gets smaller, but is still positive, so you continue to press the pedal further, but more slowly than you did before. In addition, you're starting to close in quickly on the second light, so the time rate of change of the error is getting more negative. The result is that the derivative path causes you to slow the change in pedal angle. Eventually, the error is small enough that the proportional path contributes less than the derivative path, and you start to slow the car down, and this occurs earlier than your reference position. And if you've tuned yourself properly, which loosely means that you know how to drive, then you're going to stop right at that second light. Now, one way to think of the interaction between proportional and derivative is that the proportional path tries to get you to the destination as fast as possible, while the derivative part is trying to restrain you from moving too quickly. In this case, it takes the balance of the two to properly stop at the light. Finally, let's put the entire package together and look at PID control. Let me quickly rewrite the closed-loop control system here so that we have a starting point for what I'm about to say. Now remember at the beginning I said no one drives by commanding an angle to the gas pedal. Rather, they drive by commanding a change in the angle. Well, in this example, we'll command an angle, and I'll show you why that's not a good idea. And then I'll show you how PID control can help in that situation. Let's say you're in your car and you're trying to drive right beside your friend who's moving at a constant speed. In this case, the reference signal is the position of your friend. If the output of the controller is a pedal angle, it's easy to see that there's going to be a steady state error, and you will always trail behind your friend and never beside him. Imagine this. You're some distance behind your friend and you're both going the same speed. In that case, you have an error signal that looks like this. And since the error isn't changing over time, remember that your speeds are matched, the derivative path is 0. And let's assume that the error in the proportional path causes you to press the gas pedal down to its current location. In this situation, you're not going to move the pedal at all, and you'll continue to drive behind your friend, since your velocities will still be matched. So now you might be thinking maybe your proportional gain isn't high enough. If it was, you could go a little bit faster and catch up to your friend. If you increase the gain, then the proportional path will cause you to press the gas pedal down to a new lower position, and you'll drive a bit faster, catching your friend. However, as you get closer, the error gets smaller, and so you begin to release the pedal, causing the car to slow back down again. So by increasing the gain, all you've done is shorten the distance between you and your friend, which is the steady state error. But you haven't removed the error. You can easily see the flaw in this thinking by assuming you start out at the exact speed and location as your friend, and you use a PD controller. In this case, both the proportional and derivative error terms are zero, so you immediately release the pedal and start slowing down. So by controlling pedal position and using a proportional derivative controller, we have no way of bringing the steady state error to zero. Now this is where the integral path comes in handy to remove steady state errors. When you are trailing behind your friend and the error is constant, the integral path will slowly build up error, adding more and more pedal to the output. It works like this. The error starts out constant just like it was before, and just like before, you're holding the pedal exactly where it already is and you're trailing your friend. But since the error term is non-zero, the integral path is summing up that error over time and gradually increasing the pedal's position. Eventually, as you close the gap with your friend, the proportional term will be zero. Since there's no error, you're exactly equal with your friend. The derivative term will be non-zero since you're closing the gap with your friend, but if you're closing slow enough, it won't have much of an effect on the output. But the important thing is that the integral term is going to be held constant at the exact pedal position that you need. And this is how all three terms are used to control a large variety of control problems. And I use this car example to illustrate it because most people can relate to it, and you can actually imagine the system reacting to different controllers. But keep in mind that these examples are analogous to many systems in real life. If you have a good understanding of the dynamics in the system, then it's possible to reason through the problem to determine what type of controller you need. However, choosing a controller is only part of the solution. You now have to tune the controller in order to meet your system requirements. And in these thought exercises, we really only looked at one of those requirements, and that is whether the error in the system eventually reached zero. However, in a real system, you tune the controller for much more than that. For example, you might be concerned with overshoot or rise time or settling time. And I'll cover how to tune PID controllers in future lectures, and we'll touch on each of those requirements and more. But for now, I hope this gave you a little bit more intuition on how each of these three paths in a PID controller contribute to the overall control system. And as always, thanks for watching.